Today in general, we'll be discussing on introduction to normal distribution and regression analysis. So at the end of this first section, you should be able to describe normal distribution and its characteristics. You should be able to highlight the importance of normal distribution. You should be able to describe normal distribution empirical rules. You should be able to compute and interpret normality tests on SPSS. You should be able to define reliability and highlight its types. You should be able to perform reliability and validity tests on datasets. You should be able to compute Convex coefficient alpha on SPSS. You should be able to describe validity and its types. And finally, you should be able to discuss reliability and validity in thesis sections. These are what we'll be discussing in the first section of this class. Now to start with, in one of our classes, I've mentioned, please can you mute yourself? If you have any issue, if you have any question, just draw my attention. Just send a message in box or just send a message anyway, or just raise your hand. When we say normal distribution, this is very important because majority of the data set or the kind of analysis tests you'll be carrying out will assume that your data set are normally distributed. So you have to find a way to check whether your data sets fulfill this or not. Before we know that, we need to quickly check what normal distribution actually is. So in a normal distribution, data is symmetrical, distributed with no skew. What do I mean by that? If you look at this picture I have towards the right of the screen, okay, you can see it looks like a symmetrical shape. If you have a data like this, you have a graph of your data set like this, it is assumed that your data is normally distributed. Now, it is a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. The mean is always at the middle. We're going to see more about this short while. When plotted on the graph, the data follows a bell shape. The data follows a bell shape with most value clustering around a central region and tapering off as they go further away from the center. Normal distribution are called Gaussian distribution or bell curves because of their shape. Okay, so now why do normal distribution actually matters in every research? All kinds of variables in natural and social sciences are normally or approximately normally distributed. Example could be height, birth weight, reading ability, job satisfaction, or scholastic test scores are just a few examples of such variables that are assumed to be normally distributed. So because normally distributed variables are so common, many statistical tests are designed for normally distributed populations. Okay, this is the major reason why normal distribution are quite important. Now, understanding the properties of normal distribution means you can use inferential statistics to compare different groups and make estimates about population using sample means. In most cases, the distribution of many statistical tests is normal or follows some forms that can be derived from the normal distribution. It also indicates the type of analysis that can be performed on the data. So if your data is normally distributed, there are certain tests that can be used. If it is not, there are also certain tests that can be used, which will be used. We'll be seeing those in the subsequent slides. Now, it comes with certain properties. Normal distribution have key characteristics that are easy to spot in graphs. The mean, median, and mode are exactly the same. The mean, median, and mode are exactly the same. That is, they are equal. The distribution is symmetric about the mean. Half the value falls below the mean and half above the mean. So the distribution can be described by two values, the mean and the standard deviation. The mean determines where the peak of the curve is centered. Okay, this is the mean. The mean determines where the peak of the curve is centered, increasing the move. Increasing the mean moves the curve right, while decreasing it moves the curve towards the left. The standard deviation stretches or squeezes the curve. A small standard deviation results in a narrow curve, while a large standard deviation leads to a wide curve. Now, the empirical rule or the 68, 96, 95, and 99.7 rule tells you where most of your values lie in the normal distribution. Now, if you look at this place, we have 68.3%. Here we have 95.5%, where we have 99.7%. What this means is that around 68% of values are within one standard deviation from the mean. So here, this one means that around 95.5% of values are within two standard deviation from the mean. While this was shared, while 99.7% of values are within three standard deviation from the mean. Now we're going to say much about, we're going to say some about this game. Now, using the empirical rule in normal distribution, for example, you collect SAT scores from students in a new test preparation course. The data follows a normal distribution with a mean score of 1,150 and a standard deviation of 150. Following the empirical rule, around 68% of scores are between 1,000 and 1,300. That is one standard deviation above and below the mean. Now, around 95% of scores are between 850 and 1,450. That is two standard deviation above and below the mean. Around 99.7% of scores are between 700 and 1,600. That is three standard deviation above and below the mean. If data from small samples do not closely follow this pattern, then other distribution like T-distribution, other distribution like T-distribution may be more appropriate. Once you identify the distribution of your variable, you can apply appropriate statistical test. Now, how do we now perform normality tests on SPSS? You have your data set. You want to check whether your data set is normally distributed or not. So in this example, this example shows how to test for normality with the Shapiro-Wilk test and several visuals to show if a data set is normally distributed or not. We want to determine if our pretest and post-test scores are normally distributed. Firstly, we need to create our variables. To do this, we launch our SPSS software. After launching the software, you create your variables as shown here. Excuse me. Of course, you switch to your variable view, then you enter your variable name, you specify the following properties. Then once you are done with that, you switch back to your data view window and you enter these values. So we assume that we get this following value. We took a measurement, like we took two measurements of a particular case. So maybe before and after measurements. So we take, this is for pre-test, this is post-test. So these are the values we have for our pre-test. And these are the values we recorded for our post-test. Okay, These are just sample values, okay? Just to show you, just to illustrate how to test for normality on SPSS. So in this case, we have these variables and we have these values. Now, once that is done, the next thing you need to do is to go to Analyze. Click on Analyze tab. Then you click on Descriptive Statistics. Once you click on Descriptive Statistics, you select Explore. Okay, you select Explore. Once you click on Explore, you move your variables. Remember, your variables will be here. So you move your variable into this dependent list box. Okay, once that is done, the next thing is you click on this button called Plots. Once you click on this plots, you are going to have this window. So here, you can select whatever you want, but here we are more interested in normality plot with test. So you select this normality and select this histogram as well. Okay, so once you're done with this, you click continue. Once you click continue, it will bring you back to this window. Okay, then you click on OK. So once you click on OK, you should have your output. So on your output window, we have the case processes summary. We have the descriptives, and we have the test for normality. Now, the test for normality table is the one that is quite important here. Of course, for the case processing summary, you have this information. Excuse me. You have your pre-test and your post-test. Those are your two variables. You have the total number of entries, the total number of data sets you have there, or cases you have there. Then all are 100% because there's no missing value. You can see cases missing. We don't have any missing entries. So total will remain the same. So if we have any missing value, then it will be shown here. Okay. Then for descriptive, you have all sorts of analysis. You have the mean, you have the confidence interval, you have the trimming, you have the median variance, the likes. We have for both variables. Okay. But we're only doing normality. We're only interested in the normality test. So we focus more on the test of normality table. So here, the test of normality table is the most important part. Then also, it presents two tests. We have Kolmogorov-Smirnov test as well as Shapiro-Wilk test. This Kolmogorov-Smirnov test is otherwise known as KS test. Okay, so we will go with Shapiro-Wilk test because we have a small data set, which is just 24. If you have a large data set, then you can go with KS test. Yes, please. What to check after this? That's what I'm expecting. That's why I'm expecting. Please hold on. Now, in this example, we go with Shapiro-Wilk because we have a small amount of data, which is 24 in number. But if your data set is large, then you can go for KS test. Okay. For the pre-test, we can see that the statistic value is 0.983 and the significant value is 0.946. This is greater than 0.05. Therefore, we conclude that we have normally distributed data set for pre-test. But on the other hand, if you look at post-test, the significant value is 0.006. And the low, and which is less than 0.05. Therefore, post-test is not normally distributed. Again, if you look at Shapiro-Wilk test for test of normality, the significant value for pre-test is 0.946, which is greater than 0.05. As a result of that, we conclude that pretest is normally distributed. But if you look at the other one, which is post-test, the significant value here, the p-value here is 0.005, which is less than 0.05. As a result of that, we conclude that post-test is not normally distributed. Okay, so I think I've answered your question now. This is what we use, this is what we consider for us to know whether the data set is normally distributed or not. Now, we can still follow, check other things. Remember, we have our graph. So, on our histogram for pretest, it is roughly a bell shape. Not exactly a bell shape, but we already know that it is normally distributed from what we have here. Okay. Now, if we look at the QQ plot, you can see that most of the dots on the chart, which compare the expected and observed values, are along the straight line, except for few that are not on the line. Okay, that's a good sign. If the dots are on the line, it means that the data are normally distributed. That's another way that we can get from the graph. Now, if you look at the histogram for the post-test, you will see that it doesn't by any way look like a bell shape. Even though from our normal distribution test, from the Shapiro test, we already know that this one is not normally distributed. So if we take a look at this histogram, you will see that it doesn't by any way look like a bell shape. Okay, if we look at the QQ plot, you can see that it is kind of S or snake's kind of shape. Okay, that will be typical of what you will expect for data set that are not normally distributed. That is how we test for normality in SPSS. So if you look at this place, if all the dots are on the same line, then it is normally distributed. If your histogram is a bell shape, it's normally distributed. If your p-value is greater than 0.05, your data set is normally distributed. If your data set violates any of these points, it means that your data set is not normally distributed. Okay, so this is how to test for normality on SPSS. Now, it is also very important that you check for reliability and validity of your instruments. Okay, so, and that's what led to this particular section. It is important to make sure that the instrument that we develop to measure a particular concept is accurately measuring the variable, and we actually measured the concept that we set out to measure. We need to assess the goodness of the measures developed, and the concept of reliability and validity are used to evaluate the quality of research in this case. They indicate how well a method, technique, or test measures something. Reliability and validity are closely related, but they mean different things. Reliability is about the consistency of a measure. Validity is about the accuracy of a measure. The measurement can be reliable without being valid. That is why you have to check both. If you have checked for reliability and you say that, oh, your measurement tool is reliable, the fact that it's reliable does not mean that it will automatically be valid. No, you have to check, you have to test for validity as well. So if a measurement is valid, it is usually also reliable. In this case, that's on the other side, on the other hand. So it is important to consider both tests when you are creating your research design, planning your methods, and writing up your results, especially in quantitative research. Now, when we look at reliability, reliability deals with the consistency of measurement in research. It is a quality that guarantees us that we will get similar results when conducting the same test on the same population every time. So if this result can be consistently achieved by using the same methods under the same circumstances, the measurement is considered reliable. For example, you measure the temperature of a liquid sample several times under identical conditions. The thermometer displays the same temperature every time, so the results are reliable. The doctor uses a symptom questionnaire to diagnose a patient with a long-term medical condition. Several different doctors use the same questionnaire with the same patient, but give different diagnoses. This indicates that the questionnaire has low reliability as a measure of the condition. Okay, so now we have a few types of reliability. We have test, retest, we have inter-rater, and we have internal consistency. What we have under test system, what does this actually assess? The test results assess the consistency of a measure across time. You can have a question like, do you get the same results when you repeat the measurement? A good example in this case can be a group of participants complete a questionnaire designed to measure personality traits. If they repeat the questionnaire days, weeks, or months apart and give the same answers, this indicates high test reliability. Then we have inter-rater. The consistency of a measure across raters or observers. Do you get the same results when different people conduct the same measurements? A good example could be, based on an assessment criteria checklist, 5 examiners submit substantially different results for the same student project. This indicates that assessment checklist has low inter-rater reliability. But of course, if their submission are the same, then you can say that it has high inter-rater reliability. And the last one is internal consistency, we will be looking at further. This one checks for the consistency of the measurement itself. Do you get the same results from different parts of a test that are designed to measure the same thing? A good example could be, you design a questionnaire to measure self-esteem. If you randomly split the result into halves, there should be a strong correlation between the two sets of results. If the two results are very different, this indicates low internal consistency. So we'll discuss more about this internal consistency because now, for the internal consistency, internal consistency of measures is indicative of the homogeneity of the items in the measure that tap the construct. Internal consistency reliability, this is set off, it can be done in 2 ways. One is inter-item consistency reliability, while the other one is split half reliability. For the split half reliability, it reflects the correlation between two halves of an instrument. While for the inter-item consistency reliability, which majority of researchers always use, this is a test of the consistency of respondent answers to all the items in a measure. The most popular test of inter-item consistency reliability is the Cronbach coefficient alpha. Okay, and when it comes to, suppose you wish to give a survey that measures job motivation by asking 5 questions. In analyzing the data, you want to ensure that this question 1 through 5, all reliably measure the same latent variable, which is job motivation. To test the internal consistency, you can run the Cronbach alpha test. And when you do that, if your value, your Cronbach alpha value is greater than 0.4, it is on as if it's 4 and if it is 4 and below, it is unacceptable. If it is 5 and below, it is weak. If it is 0.6, okay, and maybe little, maybe between 0.6 to 7 and go down a bit, at least it's greater than 5, okay, it is questionable. But if it is 7 if it's 7, 0.7, but it's greater than 0.6, maybe it's maybe acceptable. But of course, it can still raise some high, so it can still raise some questions. But at least you are safe if this is what you are getting. But of course, if you are getting 0.8 something, then it is good to go. And then a very good one is 0.9. So if, depending on where your value falls, you determine what you should be expecting and how you interpret your comeback, your test. Okay, I'm going to give an example now. So now I have a particular data set. Okay, so for that data set, I want to do some reliability test on that data to check whether it's reliable or not. So to perform this on SPSS, of course, you must have loaded your data set on your data view window, and to perform the reliability test, just click on analyze, then click on scale, and click on reliability analysis. So once you do that, you select all the individual items that makes up the scale and move into the item box. So here, I just want to check for marital quality. Those are some of my variables. I just move them into this place. The model should be alpha, although by default it will be alpha, okay? But ensure that it is alpha. There are other options that you can also explore that are there, but here we're looking at comeback alpha value. So once this is done, you click on statistics button. Okay, then once you click on this window will open. So under this descriptive, you select the item scale if item deleted. Then inside the inter item, you select correlation. So under the summary, you select correlation. Okay, and once that is done, you click on continue. So once you click on continue, when you have a space called scale label here, you can type any label. It's optional. Okay, it's not a must that you must write any, but just a label. Just label your output. So in this case, I just say marital satisfaction based on the kind of variables I'm trying to check the validity. So once you're done with that, you click OK. So once you click OK, you're going to have your output window. And what I put as my label will come out as scale marital satisfaction. I have my key processing summary, reliability statistics, item statistics. But I'm more concerned about the reliability statistics. And when I check the comeback alpha value, is 0.94, which suggests a very good internal consistency reliability for the scale with the sample. Okay, a number of items is 4. One by number of items is 4. We have 4 variables that was added. If you look at this place, I have 4 variables that was added here. Those are the items that I check. So, but the most important thing here is I have 0.946, which has a very good internal consistency, reliability. Okay, so this is how to check for how to do reliability test. You can also specify reliability analysis for marketing factors as shown below. I mean, depending on how you structure your questionnaire, your survey tool. So you can perform a reliability analysis for product category, for store image, for brand image, for scheme clustering, for message framing. Okay, each of these may have 3 or 4 variables, or 5 variables, 6 variables, depending on how you have structured your instrument, or depending on the theory you have adapted to prepare your instrument. Okay, so, and of course, to do this, all you need to do is, please. No problem, I will do that. So now, for this particular one, for store image, you can do something like that. Put this in. Of course, you go to analyze, scale, reliability, just the same thing. Then you can choose whatever you want and just click, enter your label and just click OK. Now, and once you do that, you have all sort of the output. For product category, you have 5 items, which give 0.727. For store image, you have 0.8 for 8 items. For brand image, there were 8 items as well. I have 0.7. For skin characteristics, you have 8 items, I have 0.79. And for message framing, you have 6 items with 0.81. Okay, so if you want to report this, of course, you can put this screenshot. You can put it in your report, or you can even put it inside you can put it under a particular appendix. But inside your report, you can have a table like this, and you can list them out, okay, and put the value, something like this. Okay, then of course you have to explain what your table is presenting. Now, that is that on reliability. Now for validity, validity is a bit harder compared to reliability, but it is even more important. To obtain useful results, the method you use to collect your data must be valid, meaning that the research must be measuring what it claims to measure. This ensures that your discussion of the data and the conclusions you draw are also valid. The validity of a measurement can be estimated based on 3 main types of evidence. Okay, validity of a measurement can be estimated based on 3 main types of evidence. Each type can be evaluated through expert judgment or statistical methods. Now, the question is, what are these 3 main types of evidence? The first one is construct. The other one is content. And the last one is criterion. Now, for construct, what does it assess? The adherence of a measure to existing theory and knowledge of the concept being measured. Example could be a self-esteem questionnaire could be assessed by measuring other traits known or assumed to be related to the concept of self-esteem, such as social skills and optimism. So when you do this, strong correlation between the scores for self-esteem and associated traits will indicate high construct validity rather. So meaning here, you may need to run a correlation test for you to know whether, so based on whatever you get, they will determine whether you have high construct validity or not. Now, the second type is content. And what does this content do? The extent to which the measurement covers all aspects of the concept being measured. Example, a text that aims to measure a class of student level of English contains reading, writing, and speaking components, but no listening component. Expert agrees that listening comprehension is an essential aspect of language ability. So the test lacks content validity for measuring the overall level of ability in English. So if a particular content or component is missing, and that particular component is an essential part of what you are trying to measure, then your measuring tool will be lacking content validity. Then we have criterion. The extent to which the result of a measure corresponds to other valid measures of the same concept. For example, a survey is conducted to measure the political opinions of voters in a region. If the result accurately predicts the later outcome of an election in the region, this indicates that the survey has high criterion validity. So these are the three types of validity that can be applied in your research. And also depending on the nature of your research will determine the one you'll be using. Okay. Now, reliability and validity in the thesis. After you have done this test, how do you report this in your thesis? It is appropriate to discuss reliability and validity in various sections of your thesis or dissertation. It shows that you have taken them into account in planning your research, and interpreting the results makes your work more credible and trustworthy. You can discuss about them under your literature review. You can discuss about them under your methodology. You can discuss about them under your results discussion as well as conclusion. But if you want to discuss about reliability and validity tests under literature review, what are you expected to say here? You're expected to discuss what have other researchers done to devise and improve methods that are reliable and valid. That is what you are expected to discuss if you are reporting this under literature review. If you are reporting this under methodology, what you're expected to discuss is how did you plan your research to ensure reliability and validity of the measures used. This includes the choosing sample set and size, sample preparation, external conditions, and measuring techniques. If you want to discuss about this under your results, okay, what you're expected to discuss is if you calculate reliability and validity, state these values alongside your main results. And if you are going to discuss about this under your discussion section, then this is the moment to talk about how reliable and valid your results actually were. Were they consistent? And did they reflect true values? If not, why? Okay, so now the reason why this place is important is because don't think that because you are getting a negative result, it means that there's no work done. There's work done. Okay, you are only paving way for future research if you are getting a negative result. Okay, that's to tell you that there's more work there's more work to be carried out in that particular domain. And that is why you have to report it the way it is. I've seen several situations whereby people try to manipulate data or change their report, all because they felt that, oh, if they see that this is a negative result, they will feel as if my research is not, I've not done anything. No, you have done your part. You have made your contribution. But it is always good for you to report a result as a statistical result, the way they appear. Don't go and transform or go and change your report because in order to suit what you actually want, report them the way they are, the way they appear, the way they turn out to be. Okay, so that it will guide future researchers. And also it will not mislead a lot of young researchers. Okay, so if you have not been able to get what you want, just stating that it has not been done, and this is the reason why it was not done. So that, and that will open up another research area for whoever that is interested to take your research to a higher level. Now, if you want to discuss about this under your conclusion, if reliability and validity were a big problem for your findings, it might be helpful to mention this here, especially if you have any negative results under your discussion. This would be a good place to mention this. Mention that here. Okay. So that is what I mean by that is how to report reliability and validity inside your thesis or inside your thesis or dissertation. If you want to, you can report under your literature review, you can report under your methodology, you can report under your results, you can report under your discussion section or chapter, you can discuss under your conclusion section. Okay, the choice is yours. Now, in summary, we need both reliability and validity in research to ensure that we have consistent and accurate answer to our research questions. Okay, the research okay. Research that reflect reliability, research that reflect reality and without reliable and correct data, which is interpreted correctly and consistently, are meaningless because it's not reliable. So if you use scores or ratings to measure variation in something, such as psychological traits, levels of ability or physical properties, it is important that your results reflect the real variations as accurately as possible. Validity should be considered in the very earliest stage or stages of your research when you decide how you will collect your data. So make sure you put this into consideration. Reliability should be considered throughout the data collection process. When you use a tool or technique to collect data, it is important that the results are precise, stable, and reproducible. Yes, please. Is there any way we run a validity test? Just like we have done for reliability. Yeah, that's why I just said now. Hold on, please, I'm coming. The reliability and validity of your result depends on creating a strong research design, choosing appropriate method and samples, and conducting the research carefully and consistently. Now, back to your question. I just mentioned something now. Please have a look at this. We have three types of validity. We have construct, we have content, we have criterion. And even before this, here I mentioned that validity of a measurement can be estimated based on three main types of evidence. Okay, and each type can be evaluated through expert judgment or statistical methods. Expert judgment could be maybe if you have a supervisor from the industry, okay, if you have a supervisor from the industry, but it also depends on the nature of your research. So if your research, if you have prepared your tool and you have an expert in that area in the industry, you can pass them your tool for them to check. So, but to be an expert, they must be a veteran in that field. Okay, and you're going to report that this is so your tool was the validity of your tool was tested using particular method. Okay, so or you can use a statistical method to do this. These are the two methods by which you can use to evaluate the validity, to check the validity of your measurement of your tool. So, and I further explain here that what are these three main types? We have construct, we have content, we have criterion, depending on what you want. The first one here, which is construct, I give an example here. A self-esteem questionnaire could be assessed by measuring other traits known or assumed to be related to the concept of self-esteem, such as social work or optimism. Then we now say a strong correlation between the scores of self-esteem and associated traits will indicate high construct validity. So meaning that you can run a correlation analysis on that particular variable to check whether it is valid or not. So based on whatever you're getting there will determine how you interpret your results. Can we use validity? I mentioned this as well earlier at the beginning of this particular section. If you look at this place. Now, if you look at this place, I mentioned it here, it is important to consider both tests when you are creating your research design, planning your methods, and writing up your results, especially in quantitative research. Okay, so if your research is quantitative, you need this. But qualitative, maybe yes, maybe. It also depends on how your tool is structured. Okay, so that is, yeah, but it's good for you to check for reliability and validity of your tools. I think I've answered your question. So, any other question regarding this? Okay, so we have come to the end of the first section. So before we proceed for the second section, I will give 5 minutes break, then we'll proceed. Okay, so 5 minutes break, then we, okay. Another thing, is there any way for check for factor analysis? Factor analysis, remind me please, I'll prepare something on that. Okay, please remind me at the end of the class. I will prepare something for you on that so that I can discuss on that with you in the next class. Okay. So 5 minutes, then we'll continue. So we'll just quickly discuss on regression analysis. I decided to combine this class because we missed our first class, right? So it's supposed to be 14 weeks. So I have to combine this with to this class. So that I have to speed up a bit. And next week is our final class as far as this intake is concerned. So we'll quickly look at regression analysis, but there's another one part of analysis that is very crucial that you need to know.
We have started an April batch, and I think next class is our last class.
That's what I'm saying. Next class is our final class as far as this intake is concerned.
That's right.
Okay, so for this regression analysis, you should be able to describe regression models. You should be able to compute simple and multiple linear regression. You should be able to highlight the assumptions of simple linear regression. You should be able to calculate simple linear regression by hand. You should be able to write regression equation. You should be able to examine independence of errors using the Watson test. You should be able to write linear regression report in APA format. You should be able to compute multiple linear regression in SPSS. Okay, so now when we talk about linear regression or regression analysis, regression model describes the relationship between variables by fitting a line to the observed data. Yes, please. No. This is, I said the last class is next week. Next week is our final class as far as this intake is concerned. If you check your schedule, you will see that next week is final class. The reason why I'm merging this together is because of the time. And if you remember, I wasn't the one that taking the first class, right? So, and I started from my own slide from second class. I need to find a way to make sure that I complete the 14 weeks. So, and that's why I have to speed up a bit. So now, what regression does is that it describes the relationship between variables by fitting a line to the observed data. That's all it does. Then we have linear regression models use a straight line. Okay, while logistic and non-linear regression models use a curved line. Okay, regression allows you to estimate how a dependent variable changes as the independent variable change. We will focus on simple linear regression and multiple linear regression within the scope of this class. So simple linear regression is used to estimate the relationship between two quantitative variables. So you can use simple linear regression when you want to know how strong the relationship is between two variables. So the relationship between rainfall and soil erosion could be a good example. We may also want to know the value of the independent variable at a certain value of the independent variable. So the amount of soil erosion at a certain level of rainfall. For example, you are a social researcher that is interested in the relationship between income and happiness. You survey 500 people whose income range between $15,000 to $75,000 and ask them to rank their happiness on a scale of 1 to 10. Your independent variable income and dependent variable happiness are both quantitative. So you can do a regression analysis to see if there is a linear relationship between them. If you have more than one independent variable, use multiple linear regression instead. Okay. Now, linear regression or regression analysis in general come with certain assumptions. Okay. Just like what we did in our previous class when we checked for some assumption as well. So simple linear regression is used to predict the value of an output variable from a predictor variable. So it is a parametric test, meaning that it makes certain assumptions about the data. These assumptions are, first, we are doing simple linear regression, which means that we are using only one independent variable or predictor. However, we can also do multiple regression using multiple predictors. The independent variable always goes on the x-axis. Both independent and dependent variable must be quantitative at the scale level. Likert survey skills can be used if the question had 5 or more item options. There are forms of regression that use categorical outcome variables, but for simple linear regression, we will only use scale variables. Regression is particularly sensitive to outliers. We have to talk about outliers in some of our, I think, three classes ago, I think I discussed about outliers. When you have a value that goes outside your data point, that's an outlier. You should identify and remove extreme outliers. To identify outliers in SPSS, check the residual statistics box after you run the regression. Here, please pay attention to this place. The bottom row is standardized residual. The minimum and maximum value should not exceed negative 3.9 and 3.29 and positive 3.29 respectively. If they don't, you don't have outliers. You should have no extreme outliers. Otherwise, delete several outliers values in the data set. How to work about this, we are going to see in a short while, and how to identify this. Further to the assumptions, the residual variance called the residual in the regression model should be normally distributed. That's another assumption. To check, create a PP plot of residual errors on SPSS or use KS test. That's Kolmogorov-Smirnov test. The residual error should be independent, not autocorrelated. The predicted residual should tell us nothing about the observed residuals. To check this, use a W-Watson test for independence of errors. The W-Watson statistics, which ranges from 0 to 4, 0 to positive 4, should be close to 2. Values that are less than 1 or greater than 3 are a problem. There should be a linear relationship between the two variables in the correlation. If there's not, then the regression will not work. The model will likely be not significant. So to check for linearity, create a simple scatter plot of your predictor and outcome variables in SPSS. If the scatter plot is not linear, if it curves or if it's cone shape, Then use nonlinear regression or transform the data. Another assumption is the homoscedasticity. The variance of the residual errors should be the same across values of your predicted errors. Please mute yourself. So, to check, scatter plot the standardized residual error against predicted error in SPSS. They should be more elliptical, not cone-shaped or curved. Otherwise, transform the data. If those are the assumptions, if certain of these assumptions are violated, you will not be able to use linear regression, but you still have options. If the outcome variable is dichotomous, that is, it's coded 1, 0 and 1, or 1, 2, or 2 and 3, or whatever, so you can use a logistic regression. If the predictor variable is categorical, you can use a t-test or one-way ANOVA, both of which are variation on that same general linear model. So let's quickly look at how this can be done. But the first time, let's see how this can be done manually. Of course, nobody wants to use manual, right? But trying to understand how it works manually will make you even understand how it works on SPSS. So in this case, we are not going to be doing hypothesis testing with regression in the same way that we have previously, that we have done in our previous practice. However, we'll be examining a model for statistical significance. The null hypothesis for regression is that the slope is equal to 0. That's the null hypothesis. In other words, the predictor variable does not significantly predict the outcome variable. So we might as well just predict with the mean. You do not need to write out a full null or an alternative hypothesis. Instead, you will state that one variable will predict another variable in the regression model. So the alpha level is typically set to 0.05, but it can be 0.01 or any other level that is chosen by you, the researcher. The regression model will be tested with an F-test and ANOVA to determine if the model predicts the outcome better than simply predicting based on the mean. The degrees of freedom are interpreted from the SPSS output. So just assume that the regression test is alpha equals 0.05 and it's two-tailed test. Now, when we are conducting a simple linear regression, we are trying to get to this regression equation, which is y hat is equal to a plus bx. So to do this, we start with the general regression equation, which is what we just stated here. And then we solve for a and b. So we will calculate the b first using this equation. This is the formula for calculating the b. B is equal to n into summation of x multiplied by y minus summation of x multiplied by summation of y, then divided by n into summation of x squared minus summation of x, the square of that value. That will give you b. Now, let's look at this. Then we will compute the mean of x and the mean of y to plug them in with a b value to the second equation below, which is this equation. So this one, the mean of y and the mean of x, and the b that we have computed earlier will give us our a. I did not ask you to enter your details, right? I don't need it for anything. You're just going to distract me, please. Both a and b will then be placed into the general regression formula. to make the regression equation specific to our research equation. You can use MS Excel, okay, as it makes the maths a little easier. So to do this, we have this sample data. Okay, so we want to compute B first. Okay, you have this sample data. You can have another column for X squared, another column for XY. Yes. So now, here you have your entry for X, you have your entry for Y. So in this case, X is being used to predict Y. So we need two additional columns. That is X squared, which is this one. Okay, and we need another column, which is XY. We do not need a square of Y for regression. So we begin by squaring each X, okay, to this place. So all you need to do is just to put equality sign here. Then you select this. Then you put multiplication. Then you select this again. Then you press enter. Or you put equality sign. You select this. Then you put caret sign. Caret sign, something like this. Then you put 2. Then you press enter. That will be computed for this. Then all you need to do is just to drag and drop. Just drag this particular cell through these ones, and that will be computed for other value of X. So then for X and for XY, all you need to do, you put equality sign here, then you click on X, this cell, then you put multiply by, you click on this cell and you press enter. Once you get the results here, just click on this page, click and hold and drag it down. Then the same will be done for other entries. Then you should have something like this. Okay. The next is to create sum for each column. You need to create sum for each column. Now, what I'm saying is that you have these values, right? For us to compute, we want to compute our B. We're trying to compute perform our regression analysis, okay? So in order for us to use this formula, this is the formula, but we need to compute for A and B, okay? And we need to plug in the value into this equation. So the first thing we do is to compute for B. The formula for computing for B is this, okay? And the formula for computing for A is this. So you need to compute for B first before you compute for A. So how do we now do this? We have these random values that we just plug in here. So inside this random value, yes, you can do, because it's just a small number of value. You can do it manually. You can use your calculator to do it, it's fine. But if you use Excel, it will be more easier for you. And that is why I'm suggesting that you use Excel. Now, to use Excel, you have entered this into this column X and Y. You need additional 2 columns, which is X squared and X multiplied by Y. Now, for X squared, all you need to do is that, to compute for your X squared, all you need to do is that you put your equality sign. Just select this cell and press equality sign. Okay, once you do that, select this cell because you want to square these values. Okay, you just want to square these values. So select this particular cell, then you can put caret, which is shift 6, depending on the system you're using. That will give you caret. Then put 2, then press enter. If you cannot do that, it's fine. Just that should work. So if you cannot do that, just say equality sign, select this, multiply by this same cell again, then press enter. That will still give you rate over 2 of this. Then you press, once you press enter, then you put your cursor at this edge. Then you click and drag it down to this place. That will generate the square of this other value for you. You don't have to do them one by one. Okay. Then for this particular field or column, which is XY, all you need to do is to press equality sign again, then click on this cell, then type asterisk, which is shift 8, that is multiply. So type asterisk and select this place, this cell under Y. Then press enter. That will give you the product of 5 and 6. So again, you put your cursor here, click on it and drag. Click and hold, okay, and drag it down. That will give you the value. That will multiply these entries and give you the result. Okay. If you have done that correctly, you should have something like this. Okay. The square of 5, 5 square will give you 25. 3 square will give you 9. 7 square will give you 49. 6 square will give you 36. 4 square will give you 16. 5 square again will give you 25. That's why you're having this. Then for X and Y, 5 times 6 will give you 30. 3 times 4 will give you 12. 7 times 10 will give you 70, and so on. That's how we got this. Now, the next thing we need to do is to sum up each of these columns. We need to sum them up. Remember the formula we are using to get our B. We need to have summation of X and Y, summation of X, summation of Y, summation of X again, and summation of X squared. So that is why we need to sum up each of these columns. So here, these are just labels, okay? Here, I want the result for the summation of this column to be here. So all I need to do is to just say equality equal to, then I click on this one. I can say plus, click on this plus, click on this plus. That is if I want to do, since it's not much. But because it's much, you can straight away use function. You can say it is equal to, then type SUM, which is sum, then open brackets, then select this, drag it down to this place, close the bracket and press enter. Then that will sum up all the entries you have in here and give you the total here. You can repeat the same thing for here, the same thing for this one, and the same thing for this one. So here we have gotten the summation of X to be 30, summation of Y to be 39, summation of X squared to be 160, and summation for XY, summation of X and Y is now 211. Now, after you have done this, the next thing is to get the mean of X as well as mean of Y. And how do we compute mean? Mean is we get the total divided by the occurrence, the occurrence of the entry, the number of the entry you're having. And if you look at this thing, we have about 6. 1, 2, 3, 4, 5, 6. Okay, so our n is 6 here. So that is why you can put the mean of X, we denote it as MX. M subscript X. And the mean of Y, we denote it as M subscript Y. Our n is 6. So to get the mean of X, we can simply say this is equal to this total divided by 6, and that will give you 5. That will be the mean. And to get the mean for this one, you can say this is equal to this total divided by 6, and that will give you 6.5. So if you look at this, we have gotten all the components we need for that particular formula. So all we need to do now is just to plug in these values into that particular formula in order for us to compute our B. Okay, so to do that, we come here, we use what is called MDES. which is parentheses, exponent, multiply, divide, add, and subtract. Okay, just like we also have BODMAS, right? Whichever one that comes to your, whichever one you are familiar with, you can always use. So, but in this case, we're using PEMDAS. So now, the order of operation begin solving the formula. So this is the formula again. So if you remember, our summation of xy is 211. So we take that value, we put it in here. Our summation of x and summation of y, summation of x is 30, summation of y is 39. 30, 39. Summation of x squared and summation of x. Summation of x will be the same value you have here. So you just put 30 here. Then summation of x squared. Summation of x squared is 160. So we put that into this place. So now when you evaluate this, you open this bracket, you multiply this by this. When you open this bracket, like 6 multiplied by 211, you're going to get 1,266. Minus 30 multiplied by 39 will give you 1,170. Then you open this one as well. This will give you now 160. Then 30 squared will give you 900. When you subtract 1,170 from 1,266, you'll be getting 96. When you subtract 900 from 960, you're getting 60. When you divide 96 by 60, you're getting 1.6. And this will be our value for P. So after we have gotten the value for P, we need to calculate for our A. Remember the formula for A is equal to mean of Y multiplied by minus B multiplied by mean of X. We have already computed our mean of X, and we have computed our mean of Y, and we have computed our B. So to do that, our mean of Y is 6.5. If you look at it here, 6.5. And our B, the B we just computed now is 1.6. We put that one in here. Okay. Then our mean of X is 5. If you remember, mean of X is 5. So that's where I fill up our equation. So now this time around, you multiply this by this, and whatever value you get, you subtract it from this place. Then you realize that you're having a negative value, which is minus 1.5. Minus 1.5 is a value for A. Now that we have our value, we know our value for A and B, we move to the next step by plugging in those values into the regression equation. So remember our regression equation, which is y hat is equal to A plus bx. So A is equal to minus 1.50 and B is equal to 1.6. So you will replace this A with minus 1.50, which is this. And we'll replace this B with 1.6. So our regression equation will look like this. Okay. Now we want to use A and B for prediction. So let's plug in X value and predict the value of Y. Okay. We will plug in some X values and predict the value of Y. Now, the first thing we want to know is what would be the predicted value of Y for X equal to 4. So if you do that, we have this equation, then we'll plug in 4 for X. So your equation will look like this. So you multiply 4 by 1.6 and subtract 1.50 because it's a negative value. So the predicted value will be 4.9. Okay, so now if someone has an X score of 4, we predict that their Y score will be 4.9. That is our best estimate. Now that you have seen how regression works, let's use a larger data set and solve the regression equation using SPSS. So now, in this example, a boss was interested in predicting job satisfaction from burnout. So an administrator at a mental health clinic was interested in predicting job satisfaction from burnout. The data set for this text are collected from 200 mental health counselors. We will predict job satisfaction among these counselors using their level of burnout, which is a loss of enthusiasm for the job. So the predictor or X value is burnout. Burnout predicts job satisfaction. Theoretically, high level of burnout will predict low levels of job satisfaction. For this example, we'll be using a simple data set called job satisfaction. I will provide you with this file so you can practice. You can use, or probably if you want it now, I can pass it to you now for those who may want to run the analysis with me. Or we just continue. Do you want the file now or I send to you later? Okay, so I'll just continue. Now, let's launch our SPSS and load the data set. Now, this is how the data looks. We have random hardy job satisfaction for GS, PO for burnout, UI, CF, CL, all this. We just have this variable. And these are the respective, some are nominal, some are scale and nominal lines. So to conduct the regression analysis, you go to analyze, okay, click on regression, and click on linear. Now, this open up the dialog box for regression as shown below. You have this linear regression. We are using burnout to predict a job satisfaction. So you move burnout into the independent box, which you have here. And job satisfaction, which is this one, to dependent box. So you should have something like this. So once that is done, you click on statistics. And once you click on statistics, you're going to have something like this. So check confidence interval, which is this one. Check this. Then check descriptives. Check Dobbin-Watson under residuals. Check case-wise diagnosis. Okay. And once you're done with that, click continue. Then, once you're done with that, you go to, it will return to something like this. So you click on plots. So once you click on plots, you move Z predicted. You move it to your X. And it is the predictor. And now, you move Z residual to Y. These are your residual errors. Then you click on histogram as well as normal probabilities plot. Then you click continue. Once you're done with that, it will return to something like this. So you just click on OK. So once you click on OK, what you're expecting is an output result of this kind. Before we interpret the output, let's check some of the assumptions for regression. That's the first thing you have to be doing. So to be sure that you have not violated any of the assumptions. Now, like we discussed earlier, regression is very sensitive to outliers. We can check for outliers in the residual statistics box, which is here. So we look at the standardized residual as they can be interpreted like a Z score. So the minimum and maximum value for the standardized residual should not exceed negative 3.29 or positive 3.29 respectively. If they do, you have outliers. If you have outliers, you stop the interpretation at this point. Go back to the data set, examine the scatter plot, and identify the outlier or outliers. You could then delete the entire case. Yes, please.
Professor, what are outliers?
Outliers, okay, for example, let's say you have a categorical variable, like for gender, for example. Okay. Actually, these are data that these are values that goes outside the values you are looking at. So let's say you use 1 to represent male and use 2 to represent female, for example. Then when you now run your program, or probably during your data entry, you mistakenly enter 10 for one of the cases as the gender. That 10 is an example of an outlier because it will affect your analysis. Because it's not within the range you are looking at. It's not within what you have used to represent your variables. You used 1 to represent male, you used 2 to represent female. And when you are keying your value, you went ahead and enter something like 10, 5, 8, 7, 20, 40, something that is outside the range you have specified. That's an example of an outlier. So those outliers are very dangerous because it has impact in your analysis result. So make sure you check, especially, and when it comes to regression analysis are very sensitive to outliers. So that is why you have to check. And how do you check? One of the ways to check is to check your standard residual values you have in here. If the value you have here is outside what you have here, then that means you have an outlier. So in order for you to now identify those outliers, you can check your scatter plot. Okay, you can examine your scatter plot because your scatter plot even your box plot. I remember I showed you something on that last week, and I told you that if you have outlier in your block, in your box plot, you will see dot at the tail, at the tail of the box itself. You will see some dots somewhere there. So I mentioned that, please, if you are not in class, please check our previous recording on that. I remember I mentioned that to you. You will know from that plot diagram, from that plot, from that box plot, you know that there's an outlier in your data set. So with that, you can go back to your data set, and either you can delete the entire case. That's the one thing you can do. That's one of the solutions that you can actually apply. It's either you delete the entire case, or you could visualize the outlier so that it has the same value as the next highest non-outlier value in the data set. So, for example, if your variable is a categorical variable of gender, for example, and you have used 1 and 2 to represent male and female. So, and suddenly you see that one of your outliers is 10 or 20. You can just change that 10 to 2. Okay? You can change that 10 to 2. Because 2 is the highest, is this next. Well, you are only considering 1 and 2, right? 1 and 2, right? So you can change that 10 to 2 to correct your outlier. So and if you do that, you visualize the outlier. And of course, if the outlier was a data entry error, we could just fix it and then rerun the regression. In this case of this particular example, we have no outliers because our range for minimum and maximum are within this scope. The negative did not go below this, and the positive, which is maximum, does not exceed this. How many times will I have to mention this, right? I don't need your name. I don't need your student ID. I don't need your email. Okay? So anyway, now, so here we don't have any outlier from this result. We have already checked the first assumption for regression. Okay? Now, next is to check the independence of observations. So next is to check for independence of observations, okay, by examining for independence of errors using the Watson test. So if you scroll down on the same page, you're going to see model summary with B superscripts. So in here, you have a model, you have R, you have R square, you have adjusted R, you have standard error of the estimate, you have W Watson. So the W Watson is close to 2. The value for W is close to 2. So here, we don't want it to be less than 1, and we don't want it to be greater than 3. But here now is close to 2. So the assumption of independence of observation has also been met. If it is less than 1 or is greater than 3, then that means this assumption has not been met. Okay. Now the next is to check for normality. Check for normality, which can be seen in the PP plot at the end of the output window. And you're going to see something like this. Then you realize that the dot generally line up along a 45-degree line. Okay, so we have a normality of residuals, and we can see that our independent variable of job satisfaction is also nicely normally distributed. If you look at the histogram. Okay, so that tells you that we have also fulfilled the normality assumption. The scatter plot of the standardized residual versus the predicted value is elliptical. As it should be, there's no pattern here, so all the assumptions have been made. I think that we need to disable this for a while. Okay, so if you look at this, you see that it doesn't follow any form of shape or any particular pattern. So the data looks great, nothing to fix or transform. So next is to interpret the regression. Okay. Now, to do this interpretation, we first check the descriptive statistic box, which is here. It provides us information such as the mean of both variables, the standard deviation, and that all 200 cases were used in this model, meaning that we have no missing value. Okay. Now, the correlation matrix here shows us that the variable correlated at negative 0.65. Okay, job satisfaction and burnout, something like this. So it's correlated at negative 0.65. This is a moderately strong negative correlation. Okay. Now, the variable entered remove, if you look at this table box, tells us that the only predictor in the model was burnout. And the only dependent variable was job satisfaction. That's what this particular table is telling us. In the model summary, we get some other useful information. Okay. First, we get the R, which is 0.65. The correlation, which is 0.65, which is, of course, we already know from the correlation matrix out there. We also get the R squared, which is 0.423. That means 42.3% of variance in the job satisfaction was predicted from level of burnout. Remember that regression, ANOVA, t-test, correlation are all part of the general linear model. So this ANOVA we have here is another way of looking at our regression model. And what this tells us is that our model with one predictor, excuse me, works better than simply predicting using the mean. So the significant value here means, the significant value here, which is the p-value here, means that our model using burnout as a predictor was significantly better than prediction using burnout in the model. There is a statistical relationship between our predictor and the outcome variable. The notes underneath the table shows how the dependent variable and the predictors. Burnout is being used to predict job satisfaction. If this ANOVA was significant, then the predictors you choose did not contribute to predicting the outcome any better than just using the mean. So now, the important part is the coefficient box, which is this. There are two types of coefficients in regression. We have the standardized and unstandardized. We have the standardized and unstandardized. For now, we stick with the unstandardized. For now, so now we need to find A and B so that we can plug them in and create our regression equation. You notice a column with a B here, but no column for A. Actually, both A and B are in this column labeled capital B. Okay, remember that A is a constant, and we already have a constant variable here. So this value of A is 235.459. That's the value for our A, because A is a constant. That will be our starting point. The value of B will be negative 2.112. Now the B coefficient has a T value associated with it. This is a T test to see if adding this variable as a predictor improves the predictive ability of the model. If a T test for the beta coefficient is not statistically significant, then that tells you that this predictor does not add to your model, so ignore it. If, on the other hand, the t-test is significant, as it is here, then look at the coefficient. Let's send in this again. Okay, look at the coefficient, look at the sign. Okay, look at the sign. Is it positive or negative? That tells you whether the dependent variable will increase or decrease due to an increase in the predictor. So here, how you interpret a coefficient is for every 1 unit increase in the predictor variable, which is burnout, the outcome variable will increase by unstandardized beta coefficient value. This coefficient is negative. So we will read this as for every 1 unit increase in burnout, job satisfaction will decrease because it's negative. Job satisfaction will decrease by 2.112 points. So the standardized beta will be interpreted as for every 1 standard deviation increase in burnout, job satisfaction will decrease by 0.65 of a standard deviation. Okay, so now, how do we now, so now that we have our A and B coefficients, we can use our regression equation for prediction. The regression equation for predicting job satisfaction from burnout is this. Remember, this is our A, this is our B. Now, for more employees are measured for burnout, what do you predict will be their job satisfaction? So using our regression equation, we plug in these X values, 25, 50, 70, and 120. So you plug them in and multiply by 2.11. Subtract that from 235.46. Your result should look like what you have here. So when you have 25 for X, your Y will be 182.71. When you have 50 for X, then your Y will be 129.96. When you have 70, your Y will be 7.76. When you have 120, you are going to have minus 7.74. Now, one thing you should notice here is that when you increase your value of X, the value of your Y keep on reducing. Okay, so meaning that the higher the level, the higher the burnout, the lower the job satisfaction. Okay, so now how do we now report this in APA style? How easily can I understand it more? It's not hard. If you fall, that's why I decided to break it down completely now. It is not hard. You just have to practice. Once you practice, you have your data. You don't have to, like I told you, I only did the manual so that you understand how it works. It's very simple. Once you have your data set, just follow the steps, then you get it done. Once you get it done, just interpret based on what I have done here. This is an illustration of how it is done. So now, how do you now report all the things we have done? The first thing you have to check for assumptions. After you check that, okay, you have not violated any of the assumptions, then you can straight away do your interpretation. And after you have done your interpretation, then you can now report. And how do you write your report in APA style is what we're about to discuss now. Now, here, you can say something like a bivariate regression was conducted to examine how well burnout could predict level of job satisfaction. A scatter plot showed that the relationship between burnout and job satisfaction was negative and linear and did not reveal any bivariate outliers. Remember, these are what we check, right? Then the correlation between burnout and job satisfaction was statistically significant. Then you put this value. This value is also you get it from the table. That's the correlation. Then also, of course, this is the correlation with 0.65, and your P is less than 0.001. Remember, your P is 0.000. So now the regression equation for predicting job satisfaction from burnout was, you have this equation, right? You understand how we got this A and how we got this B. So you key in your equation like this. Then the R square for this equation was this. You get this from your regression table as well. Then that is 42%. 42.3% of the variance in job satisfaction was predictable from the level of burnout. This is a moderately strong relationship. Here, you can have this particular reference, or you can look for a more later reference. Okay, that is if you really want to put this particular reference apart. But this is a claim. That's why I put this reference. Now, the bootstrapped 95% confidence interval for the slope to predict job satisfaction from burnout range from minus 2.5 to 1.77. Thus, for each 1 unit of increase of burnout, job satisfaction decreases by about 1.8 to 2.5 points. So now, what is the component of this? What is the content of this report? The first thing we did was to explain what test was done. And that's why I said a bivariate regression was conducted to examine how well subsidy was done. Then what were the results? We see what the results were. We report what are the results we got. Then we include the regression equation and the R square and the interpretation of what that means. Okay, that's exactly how to do simple linear regression. It depends on the nature of your research. Okay, if some of your research, you may not need it. Okay, you may not need regression analysis, and that's why I said in the very first slide, I mentioned it here that if you want to check, you use regression model to describe the relationship between variables. If you want to investigate relationship between variables, then you use regression analysis. Okay, it also depends on your research. Okay, so but if your research involves you to use regression analysis, then definitely you need to do this. Okay, so now so that is how to report a simple linear regression. Now, that is just a simple one. You may even have multiple linear regression. Now, let's look at this example of multiple linear regression. We use multiple linear regression when we have a continuous dependent or outcome variable, and when you have two or more continuous independent or predictive variables. Multiple linear regression can be used if you want to know whether variation in a dependent variable or outcome variable can be predicted by independent or predictive variables. So in this example, let's assume that we have conducted a little study where we are interested in whether we can predict how often someone is late to a lecture within a given year by how far they live from the campus and by how far they live from their nearest train station. For those of you who will be doing predictive analysis, definitely you will need linear regression. So now, to do this, we launch our SPSS application and create your variables as shown here. So we have three variables. One is distance campus, distance train, time late. So we just separate those word by underscore. Then we assign the following variables. So a continuous variable is a variable whose value is obtained by measuring. Example can be height of student in class, weight of student in class, time it takes to get to school, distance travel between classes, and so on. Those are examples of continuous variables. Now, after you have created those variables, then you can enter this sample data set. Okay, then to perform the regression analysis, you go to Analyze, click on Regression, and click on Linear again. So once you have done with that, that will bring you to this window. So here, you move the independent and predictive variable into the independent box. Move the dependent variable or outcome variable into the dependent box, just like this. So once this is done, you click on Statistics button and select Estimate, Covariant Matrix, Model Fit, Descriptive, Collinearity Diagnostics, and click Continue. Once you are done with this, you click on Plots, okay? And you select your Z residual, you place that one on your Y, and you put use set print, you put this one on hex, then you just make sure you click your normality probability. Then if you need the histogram as well, you can click the histogram if you want. Then, but for now, we are not using any of this. So just click Continue. Then once you're done with this, then there's another button here called Save. So you click on Save button. This will open this place for you. Then you select Cooks. We are selecting all these options because of the assumptions that comes with multiple linear regression. These are what we are going to be using to check whether those assumptions are not violated or not. So after you choose these Cooks, then click on Continue. And once you click on Continue, then you will come back to something like this. Okay, so just click OK. So once you click OK, you're going to have your output window. Yes. So one of the assumptions that is there, one of the assumptions is that there is no strong relationship between the predict or independent variables. So in this case, the predicted variables are distance from campus and distance from train station. So if we check the correlation box, which is here, okay, or the correlation, the hard value between distance from campus and distance from train is negative 0.177. And normally the cutoff for determining whether the relationship is too strong or not is positive 0.7 to negative 0.7. So since our value here is closer to 0 than 0.7, we can conclude that there is no problem with multicollinearity. Okay, so there is no too strong relationship between the predictor variables. That's the first assumption. That means we have met, that one has been met. So hard values representing the relationship between the predictors is closer to 0 than 0.7. And negative 0.7 are shown in the correlation table, which you can see here. Now, that one has been fulfilled. In the coefficient table, the tolerance value is above 0.1 and VRF is below 10. Okay, the values of the residual are independent, as shown in model summary table. The value of Doban-Watson is between 1 and 3. Now, the value of the residual are normally distributed. Evidence of this is shown in the PP plot. The dots in the normal PP plot are close to the line. A lot of them are on the line, even though some of them are not, but we still assume that they are normally distributed. Then the assumption of homoscedasticity was also made. No obvious pattern in the scatter plot shown below. That's another one. So there are no influential cases biasing the model as the maximum Cook's value. As the maximum Cook's value is below 1. It's below, this is 0.105. So it's below 1. So under the residual statistics. Now, so we can conclude that that no cases are having an undue effect on the accuracy of the model. This might happen if we had very high or very low score associated with certain participants. So you just want to check that it's not happening. And this is another way to check for outliers. Okay. So now this is done. Next is the regression analysis itself. So the first thing people often check is the R-square value under the model summary. In this case, it is 0.467. So that means that the model predicts 46.4% of the variance in independent or outcome variable. So if we check the ANOVA table, we can see that this is significant because we have 0.000. So the model predicts a significant amount of variance in the outcome or dependent variable. In addition to checking whether the model, which contains both predictors is significant, we can check the individual predictors as well. So if we check through the coefficient table, we can see that the distance campus variable row that we have, that we have a p value, a significant p value, then so that suggests that distance from campus predict a significant amount of the variability and how often someone is late to lectures. Similarly, with the distance from the train station, the p value here is less than 0.05. So we can conclude that the distance someone lives from the nearest train station also predicts a significant amount of variance in how often they are late to lectures. Okay. Now, how do we now report this? This is another method you can use to report. You can say, to ensure that there was no multicollinearity, a Pearson correlation coefficient was calculated to examine the relationship between the predictors. The coefficient R, negative 0.18, you see this from your coefficient table, suggested that the assumption of multicollinearity was not violated. Moreover, tolerance 0.97 and variance inflation factor 1.03 values did not indicate a violation of this assumption. A W-Watson statistic was calculated to assess the assumption that the values of the residuals are independent, which suggested that this assumption was not violated at 1.78. A scatter plot was created to assess the assumption that the variance of the residuals was constant, that is, homoscedasticity. The plot did not indicate a violation of this assumption. Then you can now attach the plot. Okay, maybe a screenshot of it in an appendix. Then you can reference the appendix as Appendix A. Then a PP plot was created to assess the assumption that the values of the residuals are normally distributed. The plot did not indicate a violation of this assumption. You can take a screenshot of that as well and put it under a different section of your thesis and name that Appendix B. Then you can do some kind of intercitation by putting this Appendix B. And I've already shown you how you can make this an hypertext, right? Whereby when your user when your examiner or your reviewer click on this, it will take them straight to that appendix. Distance values were calculated to ensure that no influential cases were biasing the model. All values were below 1, suggesting that no cases were biasing the model. So these are the assumptions you have checked. Okay, you have checked, you report that you have checked the assumptions. Then this is now when you are reporting the results. So a multiple linear regression analysis using the enter method was conducted to examine whether how often individuals are late to lectures can be predicted by how far they live from campus and how far they live from their nearest train station. The model was significant. You have F, then you have 2.27. This higher degree of freedoms. Maybe I just show you this one very quickly. All these values are from those tables, but let me just show you this one. So this is F. The value of your F is 11.77, and your degree of freedom for your regression is 2, and your degree of freedom for your residual is 2.7. So 2.27, this one we got it. So we have this one, and the value of the F is here. They will say P is less than 0.001. Then explaining 46.4% of R, you have your value of your R coefficient earlier is equal to this of the variance in the outcome variable. Both distance from campus, then you have your B to be equal to 0.62 and T is equal to 4.53, P less than this. And distance from train station, you have this as well, this value also contributed significantly to this model. So this is how you report this particular regression analysis in APA format. Okay, so that is that on this. So if you have any question, please let me have it. So I have shared the attendance link in the chat. So please fill up and submit. Okay. So if you have any question, please let me have them so that we can discuss. Okay, in the absence of none, we have come to the end of today's section. I will share the notes. I'll share the slide in the group, and I'll also share the recording link as soon as it is ready. So you can always go through and watch the recording again. And again, I also use this medium to remind you, next class will be our final class for this particular intake. So I want to believe that we have been able to touch all the areas we're supposed to touch. And if you have any issues, you can always refer back to the class recording as well as the slide. So I hope you can apply this in your research work and move fast and complete your work as soon as you can. So thank you and stay safe and see you again in the next class. Bye.
Thank you, Dr. Munir.